Welcome to the fourth presentation in the third webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube. This is the fourth webinar of our third series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the third series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Professor Sebastião LUCENA of Federal University of Ceará in Brazil. I'm Nicholas Wilkins of the University of Alberta in Canada. Today's webinar will be moderated by David Donacci at Imperial College London in the United Kingdom. We were requested to remind attendees and future viewers that the views expressed by the speaker, host, and other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member, if you are not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsoats for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. The IAS will host the 14th International Conference on the Fundamentals of Adsorption in May 2022 in Broomfield, Colorado, near Denver. The conference will cover all aspects of adsorption, ranging from fundamentals, process applications, green energy, among others. Beyond the scientific content, the setting is outstanding, just downhill of the mountains of Western Colorado, which will allow for excellent side trips and excursions. Registration is open and can be found by following the link on this page. There's also a virtual attendance option, with certain portions of the program broadcast live and all other oral presentations available in a pre-recorded format. I'll now hand it over to David Donacci, who will moderate the Zoom Q&A.
Thank you very much, Nick. It is my pleasure to introduce our speaker today, Sebastião LUCENA, who is an associate professor in chemical engineering at the Federal University of Ceará in Brazil. His PhD was done in chemical engineering at the State University of Campinas, Brazil, with a research internship at Northwestern University in the United States with Dr. Randy Snow. Dr. LUCENA's master's is in material science and engineering from the Federal University of São Carlos, also in Brazil. He was the head of chemical engineering and the coordinator of the graduate program in chemical engineering at UFC. His research interests include molecular simulation with an emphasis on adsorption and transport properties methods based on statistical mechanics, using methods such as Monte Carlo and molecular dynamics, molecular simulations on novel adsorbents for CO2 capture, and the characterization of materials for energy storage and separations by adsorption. During the webinar, questions can be submitted to the speaker in two ways: via the Q&A tab of Zoom for those joining us there, or as comments on the YouTube live stream. I'll then forward those comments on during the Q&A session. With that, I'd like to hand it over to Sebastião now, who will take it away.
Sebastião, do you mind turning your video on as well? And your microphone.
Okay. We think now you can hear, right?
Yep, everything's good now.
Okay. Good morning. Thank you, David, for the kind introduction. In this presentation, we're going to talk about two sets of papers. I split the presentation in two parts, lasting approximately half an hour each. The first part is about two articles that show the evolution from our first heterogeneous models to the current model based on reactive molecular dynamics. The second part will be about the application of the reactive model. Then we start now the first part from the first idea of heterogeneous models until the actual model using reactive molecular dynamics. Let me show you why you choose to investigate heterogeneous models. In 1989, Seaton, Wharton, and Quick proposed slit like homogeneous pores to perform kernels of local isotherms for characterization. They use a first version of the mean field DFT theory. In 1993, an improvement of the theory was introduced, the non-local DFT. After that, the slit-like pores become central to characterization technique, being very useful until now. However, as more and more materials were characterized, a persistent gap of carbon pores in the pore size distribution and a poor data correlation became evident. This is described, for example, in the study of Oliver in 1998, where they claim a mode-induced artifact by homogeneous models. In the next decade, from 1988 until 2009, many studies were performed about how to introduce heterogeneities until the first heterogeneous kernel proposed by Neymark in 2009. They include implicit heterogeneities based on a Ragness parameter in one dimension. The method is known as quanti-solid DFT, QS-DFT. In 2013, Jaello and Oliver also proposed implicit heterogeneities based on periodic variation of superficial energy in two dimensions. The method is known as 2D and LDFT. The introduction of heterogeneous kernel that you name second generation kernel open up opportunities to find out how you can correlate the implicit heterogeneities with real defects found in carbon materials. These studies of virtual carbons and kernels can be grouped by defect species like corrugation, like this we show here, edges, and some highly amorphous representation of the carbon. This is why our lab efforts concentration these models, particularly in the edges heterogeneous models. Edges can be obtained in different ways. Seaton in 1997 proposed that we select a random carbon atom in the innermost layer and delete, just remove it. They delete from 5 to 75% of atoms. They do also propose a random selection of atoms, but now, besides remove the atom, all surround neighborhood atoms that have distance less than an effective defect radius are also removed. They do delete from 5 to 55% of atoms in the innermost layer. The reverse Monte Carlo method can also be considered an edge method Sheets of graphene are arranged in the simulation box, reproduce the experimental radial distribution function of the material. In the final model, the adsorbate is interacting with edges in a considerable pore volume of the material. Ceton, for example, could reproduce experimental diffusion coefficient ratios between oxygen and nitrogen. They do reproduce isosteric heat of spharon carbon black series, 5 different samples. And Thompson and Gubbs could reproduce nitrogen isotherms of activated carbon A, MC, and B. When we start this research, no kernel incorporating edges had been designed. Our first experiment was to introduce a limited number of pores with edges in the pre-existing homogeneous kernel. When you use a homogeneous kernel, this picture, a surface of a homogeneous kernel. Our reference kernel has 24 pores. We can observe when applying this to the experimental nitrogen isotherms, we can observe a PSD gap that you have mentioned here, the gap. And also a poor correlation between experimental and simulated isotherms. You can see a poor correlation here between the two isotherms. To verify the effect of edged pores, we introduce a total of 6 heterogeneous pores with two sizes, 13.4 and 15 angstroms. Each pore had versions with 25, 50, and 75 of carbon delete. With just these 6 heterogeneous pores, the gap was eliminated. You can see that this gap doesn't exist anymore. And the correlation between isotherms was very good, the simulated and experimental isotherms. This result gave us confidence to elaborate a complete edge kernel with different degrees of heterogeneity, which you can name multi-kernel. Let's take a look in the multi-kernel. A particular characteristic of our multi-kernel is that besides different degrees of heterogeneity, 25, 50, and 75, we also include the homogeneous kernel. This will increase the significance of the kernel. The kernel has therefore a total of 88 local isotherms. We elaborate maps, energy maps, to compare our homogeneous and heterogeneous surfaces. You can see how the heterogeneous surface present patches of different energies, while the homogeneous surface has uniform energy. Here you can observe how the multi-kernel eliminates the pore gaps and improve the data correlation between experimental and simulated isotherms for the carbon PC58. If you apply only homogeneous kernel, you obtain a pore size distribution with gap and a poor correlation between simulated and experimental isotherms, like you can see here. When you apply the multi-kernel, you can see a continuous pore size distribution and a very good fit between experimental and simulated isotherms. The multi-kernel approach introduced complexity to the pore size analysis, because before you had only one kernel, now you had 4 different kernels. We figure out how to present this information to be easily understood. We split the different kernels in sums of the volumes. Then for the activated carbon PC58, we have 26% of the volume that comes from homogeneous kernel. 31% that comes from the etched 25, and 29% that comes from etched 50, and 14% that comes from etched 75. We realized that now you can measure the heterogeneity of the material. For example, in the activated carbon PC series, as the burn-off increase, this is how the burn-off increase from PC12 to PC65, the volume of the homogeneous kernel decreased from 42% to 20%, as we expected. We also found that the multi-kernel is useful to discriminate heterogeneity in surfaces. This is helpful because topological defects in graphene are investigated with costly techniques like high-resolution transmission microscopy and scanning tunneling microscope. We compare two carbon blacks, the BP280 and carbon pack F. BP280 is a standard heterogeneous surface, and carbon pack F is an ordered surface similar to graphite. We found that the multi-kernel gives only 4% of homogeneous volume for BP280, while it gives 77% of homogeneous kernel to carbon pack F. It's a very interesting result because you can see how a surface can be analyzed. With this successful results, we focus on developing a more natural strategy to create edges. From the beginning, when we started to delete atoms, we wonder if there exists less empirical method to perform the task. This became possible after two developments in the molecular reactive force field Reactive. The Reactive was developed in 2001, but only in 2008, an optimized reactive force field for carbon combustion was introduced. This is a graphical representation of the combustion. Oxygen and graphene sheet stay in contact after a little time. All graphene sheet is oxidizing. Then you see the steps here. But this combustion force field of 2008 was validated in a series of experimental systems, but a surface from the force field cannot be used for adsorption studies because they present countless unstable structure. This is a kind of a structure that comes from the combustion force field. We have a lot of unstable structures like unstable carbon rings and a lot of linear carbon chains. When an optimized surface for carbon condensed phase was developed in 2015, then we finally could apply reactive molecular force field to mimic the real process of obtention of activated carbon. Because now you can perform regularization of the surface that comes from oxidation step. Then use the combustion to arrive in the surface, and after you apply the carbon condensing force field to make the surface regularization. Now you can apply adsorption in the surface. The result is that the previous random process of delete atoms is replaced by a chemical reaction of oxidation guided by reactive molecular dynamics in 2 steps. And the first step is oxidation, and the second step, regularization. Here is how it works. We build a simulation box with 1,000 oxygen atoms and 3 layers of graphene with 38 to 39 angstroms. The first layer, here the first layer, is frozen, and the other layers are free to move. This is a move of the oxidation step. The first impact of oxygen molecules transfer energy and almost any carbon is consumed. This phase lasts approximately 20 picoseconds and is the blue area in the graph. This period is named the induction phase. Here in the Biliary, the induction phase. After that, the surface enters in the self-acceleration phase that lasts approximately more 20 picoseconds. Now you are starting the self-acceleration phase that you have some reaction between the oxygen and the graphene surface. Finally, the terminal phase starts when approximately 35% of the carbon atoms were consumed. We believe that now the terminal phase is starting in the move. We believe that once the material enters in this last phase, the reaction cannot be stopped. This will bring consequences in the multi-carbon model that we will discuss further ahead. After the oxidation step, we perform the regularization step. Here is a short movie of the regularization step. Note that the unstable carbon rings and linear carbon chains are eliminated from the surface. The carbon proceeds in a sequence of reorganization until the more stable configuration. Okay, these are the energy surface maps after regularization step with 5%, 10%, 55%, 25%, and 50% of the carbon atoms consumed. We test each of one this surface against isotherm of standard carbon black BP280 and LME10 used in the validation of quantisolid FT and 2D and LFT kernels. We obtain the best result with the surface whose carbon atoms were oxidized in 25%. So this surface with 25% is the best surface to reproduce the experimental result from carbon blacks BP280 and LME10. Before examining the isotherms in the reference materials, it is interesting to take a closer look in some details of the model. In this figure, we mapped some carbon rings defects. 5 carbon rings are in blue color, 7 carbon rings in pink color. Because these defects in the end of the oxidation process, the model incorporates not only edges, but also corrugation that induce a certain degree of amorphizations. The picture on the right is a snapshot of nitrogen adsorbed in the surface. A side view, a front view of the nitrogen atoms adsorbed. Here are the isotherms fitting results. As you said earlier, the best match was the 25% oxidized carbon surface. When you compare quench solid FT, here quench solid FT, the black line, to the annual FT, the red line, the experimental data, the blue circles, and the reactive model, the orange circle. You can see that the reactive model performed very well. This is for BP280 carbon and for the LMA10 also. The quench solid FT is the black line, the experimental data is the purple line, and the origin, the purple circles and the orange circles is the result from the reactive model. A second test was performed with experimental isosteric heat of carbon black Stirling 1500. Again, with a superior performance of the reactive model. Compare with quench solid FT is the purple line, and another explicit heterogeneous model named Humpled model, the green squares. In the black cross is the experimental data, and the orange circle is the result obtained by our reactive model. One last observation: is it important that the method of oxidize with reactive force field result in the surface with similar performance related to adsorption? So we tested 10 different iterations until oxidation of 25% of the carbon surface. And you can see that we obtain similar results here in the for the isotherms. We obtain similar result for the isotherms, and also similar result for the isosteric heat. This demonstrates that the reproducibility of the technique is good, right? Because you make 10 different iterations and you obtain very similar results of the surface. Okay, here we finished the first part of the presentation. Then if you have any questions.
Thank you very much, Sebastião, for the interesting talk for this first half. So just a reminder to everyone, you can leave questions in the YouTube chat or on the Q&A tab in Zoom. While those are coming through, I had one from Nicholas Wilkins, who is asking about how the carbon structures are obtained, and when you do the Reactive simulation. Do you just do one of those simulations for the combustion, or do you do multiple simulations and then average them together?
We make an average of the 10 iterations that you show in the last picture. I think.
Yeah, I think your last slide answered his question.
Okay.
Thank you. Thanks very much for that. A question from me. Now that you have generated this heterogeneous structure,
okay,
have you attempted to do other kinds of quantum mechanics or molecular dynamics simulation to see if you can see impacts on physical properties like heat capacity or thermal conductivity? And can you see an impact on those based on the heterogeneity of the material?
This is a very good question, because one thing we thought you can do is to use Raman spectroscopy to analyze the surface. And you can match the Raman spectroscopy with the isotherms, but until now you could perform this kind of investigation. But it's a very good idea to do with this model. We didn't do something like you propose.
No, but that's okay. It's good to see or hear that the agreement with the Raman is there.
Yes, because you can simulate a Raman also, and you can match experimental and simulate that in both sides between Raman and also absorption.
Thank you very much. I don't think we have any further. We have one question from the audience here on Zoom. It's from Marco Amandi, who is asking, if you have heteroatoms in the carbon, such as nitrogen doping or potassium intercalation, have you attempted to use these models for materials like that?
Yes, it's another it's another procedure that you can implement, but now we have a limit in the reactive force field. Now the reactive force field deals only with carbon atoms. Then we did develop new reactive force field that can cope with another atoms different from carbon. There is another area interesting to investigation, but first you need to develop a reactive force field with the new atom space that you will mixture with the carbon atoms.
Right. Thanks very much. Yeah, that makes it. He says thank you in the
Thank
Q&A
you.
there.
Thank you for the question.
With that, I think if you're happy to, we can continue on to the second part of the presentation.
Okay, let's continue with the second part. In the second part, we deal with studying cooperation with Alex Neymark, where you compare the performance of a complete kernel of reactive model with Kent-Solid DFT and some new investigation. We also will present some new investigation that can expand the kernel application. Before we discuss the pore size distribution, because now you made a complete kernel of the reactive model, it's interesting to pay attention in some local isotherms of selected pores. For small pores like 7 angstroms, we found the highest variation between Kent-Solid DFT and our reactive model. As you can see here, the red line is Kent-Solid DFT. The blue dots are the reactive model. And you also show the homogeneous for reference. When you increase the pore size of 27.9 angstrom, the variation between Kent-Solid DFT and reactive model decrease, the divergence decrease. But we can observe some difference. The Kent-Solid DFT is the red line. The blue dots are the reactive model. You can see difference. And the homogeneous we also present for reference. Well, here is the aspect of the complete reactive kernel of isotherms. And now we analyze again the same activated carbon before the PC58 that was previously presented in the multi-kernel section. Our reactive kernel present perfect fit between experimental and simulated isotherm, just like the quench solid DFT also present a perfect fit. With the naked eye, you can see difference between quench solid DFT and reactive molecular dynamic fitting. So we need a graphical representation of the absolute error to see the difference. Then you present this graph of absolute error, then so you can see the difference between the two fittings. The reactive model is the blue line, and the quench solid DFT is the red line. And you can see that they have both a good presentation. Here you have both pore size distribution. The pore size distribution from the reactive model is the blue bars, and the pore size distribution from the quench solid DFT is the red bars. A significant observation of this pore size distribution is that the quench solid DFT do not present gaps, while the reactive model present pore gaps. And you believe that those discrepancies in pore size distribution are consequence of the nitrogen isotherm divergence in the small pore range, like we showed previously. It's also important to note that although we obtain an excellent fit between experimental and simulated isotherm, this fit did not guarantee the absence of gaps. It's a interesting observation. With an implicit heterogeneous surface, you can test different models of nitrogen or other gas molecules, united atoms and atom-atom models. This cannot be done with DFT models. It is an opportunity to test a hypothesis from DDU previous study that show large discrepancies in pore isotherms if you use united atoms or atom models. In this graphic from DDU study, you observe that the same pore, the 6.5 angstrom pore, fuse in very different pressure. The atom-atom model fuse first.
Sorry to interrupt, Sebastião. I think we have lost your audio.
Nitrogen models with the reactive surface. The film impression difference vanish. You can see the difference disappear. We conclude that the film pressure difference that is observed here is caused almost exclusively by the homogeneous surface. This is a kind of artifact of the homogeneous surface. A partial conclusion of the reactive molecular dynamic kernel is the pore size distribution suggested by both reactive model and quench solid model provide good correlation between simulated and experimental isotherms. But the quench solid DFT proved to be very efficient, allocate pore size more evenly without gaps. And heterogeneity in carbon wall decrease the nitrogen isotherm discrepancy between different kind of gas models like united atom and atom of nitrogen models. Here we discuss some extension of the multi-kernel application. The first idea to expand the reactive model is to design a new multi-kernel. This is the first idea, is how we can make a new multi-kernel. You remember that according to the steps of the reactive molecular dynamics model, it's unlikely that you can find etched structures with more than 35% of delete atoms, above 35% of carbon oxidation. The graphene surface enters in the terminal step where the reaction cannot be stopped. Then we didn't believe that highly etched surface like 55% or 75% exists. You cannot use highly etched surface. We realize that some rules are important to guide the multi-kernel design from now. The first suggested rule is that the multi-kernel needs energy diversity. Here you can see two energy distribution of carbons. The carbon A is more heterogeneous than carbon B because it represents a large energy variation and above and below the homogeneous energy reference. The homogeneous energy reference is the dot red line here. In the carbon B, the energy is very close to the red line. This is why carbon B is more homogeneous than carbon A. The multi-kernel, therefore, needs to reflect this energy variation among carbons. A suggestion on how to implement the energy diversity might be as follows. Here are the isotherm surface of different carbon models. The blue circle, this isotherm, the blue circle, is the homogeneous model. The green circle is our reactive model. You can see that the reactive model adsorbs more than homogeneous model. Consequently, the reactive model has high energy level. Then they position in the right side of the energy, the side of high energy. Here, the homogeneous energy, here the reactive energy. To represent the low energy range, you can use a model with parallelographene walls, but you can use another kind of model to low energy. I think it doesn't matter which structure you choose to represent low energy. It's important that the structure has low energy. The yellow isotherms come from this kind of model, the low energy. Then with these three subkernels, high energy, homogeneous, and low energy, we think we fulfill the diversity energy. Our second suggestion is about a method to test pore size distribution. As our objective is to obtain a pore size distribution, the only carbon that I know a priori the pore size distribution is a virtual carbon model. Then virtual models can be used as a testing tool. To illustrate the approach, we take this virtual carbon model from Kumar. The virtual carbon nitrogen isotherms, the white circles here, is now our experimental isotherm. We have observed that the quanti-solid DFT, the green line, present a poor fitting with the experimental isotherms, while the multi-kernel fits perfectly. The red line is the multi-kernel fits perfectly. If you to evaluate the pore size distribution performance of each kernel, we first calculate the real pore size distribution. Is the black line. We use the pore blaze code to make this. The black line is the real pore size distribution from pore blaze. Then, after perform pore size distribution in both kernels, we found the proposed multi-kernel pore size distribution from quanti-solid is the green line, and from the multi-kernel is the red bars. We observe that both kernels reproduce the pore range. There's no doubt about this. Predicted by pore blaze code, but the multi-kernel present a better fitting than quanti-solid DFT for a smaller pore around 10 angstroms. You can see that the quanti-solid distribution starts here, and the quanti-solid didn't see this volume of pores around 10 angstroms. Well, we also test real carbon with the new multi-kernel. We choose the carbon Desorex. This carbon is from the German company Donau. This carbon is a mixture of bituminous carbon and coconut shell as raw material. And curious, both reactive model and quanti-solid model did not perform well in this carbon. Here is the isotherms, the experimental and simulated. Here is the absolute error. You can see that with the absolute error, both isotherms have from reactive model, the blue one, and quanti-solid model, the red one, had some problem to fit these isotherms. If you observe the pore size distribution, the blue bars is the reactive model and the red bars is the quanti-solid DFT. You can see that both models shows gaps around 10 angstroms. When you analyze with the new multi-kernel, the green bars, we observe almost a coincidence. The multi-kernel is almost coincide with the zero error. The line is the green line is coinciding with the black line of the zero error for all interval of pressure. And the pore size distribution, the green bars, we observe a uniform distribution with any gaps. There's a very interesting result for a real carbon. Another application of the multi-kernel would be in the dissection of heterogeneous isotherms obtained by DFT in terms of elements embedded in the multi-kernel, like homogeneous, reactive, and low energy. You remember that the quanti-solid DFT and the red line, in the reactive model, isotherms in the pores of 7.7 angstroms are different. One hypothesis would be that each quench solid DFT isotherm incorporates different characteristics of heterogeneity. This hypothesis can be tested using multi-kernel, for example. Here, this 7 angstrom quench solid DFT isotherm. We apply the multi-kernel analysis of this isotherm. We obtain that it has 78% of homogeneous character, 16% of the reactive character, and 7% of low energy. When as the pore increase to 8.9 angstrom, the homogeneous character decrease, and while the heterogeneous character, both for both reactive and low energy, increase. In larger pores, like 18.5 angstrom, the heterogeneous character of reactive model reach a maximum value, while the homogeneous goes to a minimum value. This model of analysis is interesting because it assigns quantitative parameters to explicit defects characteristics that are built into the different heterogeneous DFT-based kernel. It can be used to quench solid DFT or 2D linear DFT, both heterogeneous proposals based in DFT. Here we finish the second part. I invite all of you to visit our site lab3dufc.biliary, and you'll find the web application, the characterization tab, that perform pore size distribution calculation with all the kernel present today. Thank you, and questions for the second part.
Thank you very much again, Sebastião, for the very nice results you showed here in the second part as well. Just a reminder to everyone, questions can come through the YouTube chat or the Q&A tab on Zoom. And while we are waiting for those, Nick Wilkins has a question. The first part is it possible to generate kernels at higher temperatures so that you can use, ambient temperature isotherms to generate pore size distributions? And related to that, or to estimate adsorption isotherms, so to do the reverse problem, once you have the pore size distribution, to then estimate an ambient temperature isotherm.
You are asking if you try to do this?
Yeah, or have you tried to do it, or is it possible or sensible to do that?
Yes, it's possible. We now are trying to do also to change the gas. If CO2 isotherms can predict nitrogen isotherms, or a nitrogen isotherm can predict CO2 isotherms, and something like this. We are now working in this kind of investigation.
Okay, thank you very much. You mentioned that, and I have a related question to the other gases that you mentioned. We've seen in the past few years, and also very recently, papers where they combine multi-gas kernels instead of the current approach, which is
yes, this is also a proposal that Jaielo is working.
They're the ones that I was referring to.
He is combined CO2 with nitrogen. I think he combined also hydrogen.
Hydrogen and oxygen was
hydrogen
another,
and oxygen. Our first try in reproduce from different gases. I think you can now try to do this simultaneous prediction using different gas kernels to predict one part size distribution. This is also a very interesting line of investigation with this heterogeneous kernel. But you right. Didn't yet.
No, thanks very much for answering the questions. Let me just confirm. Where is? Okay. There are still no further questions on YouTube, so I will ask another one in the meantime, which is, you've kind of shown a very nice way to estimate the heterogeneity from these isotherm fittings.
Yeah.
Do you think it is possible to extend the application to things like tracking combustion, or things like biomass gasification or coal gasification, to use isotherm analysis as a way to characterize the combustion, let's say, in those processes?
Yes, you really believe in this. We want to try to do this first with surface, because you can control the burnout in the surface. For example, we think that you can start with a graphene surface and then etch this graphene surface, oxidize this graphene surface in the lab, experimental, and measure the evolution of defects, and you see the heterogeneity grows as the reaction with the surface increased. I really do think that this can be done. This is a new application for this kind of kernel.
Thank you very much. That's interesting to hear your thoughts on that. Okay. With that, I think we will. There don't seem to be any further questions, so we will wrap up the webinar. So I'd like to thank Sebastião again for your very nice presentation.
Okay, thank you. Thank you also.
I'll hand back now to Nicholas, who will wrap up and give the information for the next upcoming webinar as well.
Okay, bye.
Thanks again.
Thank you.
Thank you, Sebastião LUCENA, for your presentation on recent developments in the characterization of carbon materials. We also thank all of the attendees for joining this webinar and hope it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel with an announcement on the IAS Twitter feed. The hope is that the work discussed today will be a useful resource for the adsorption science community in the future. At the moment, we don't have an upcoming IAS webinar, but it will likely be after FOA 14 in June. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing lists. With that, we thank you for joining us, and we hope that you'll join us again soon.